Hello students, hope all is well. Here's a very brief video to illustrate the Newman projection. This is found in your chapter 3 of McMurray, and that's been around since I was an undergraduate. It's named for Melvin Newman, the late Melvin Newman, a chemistry professor who was at Ohio State and worked almost until 90 years old. In the days before computers, this is still used, incidentally, the Newman projection. In the days before computers, it was a way to get you to look at non-bonded groups that are in close proximity by single bond rotation, but are not connected to each other. Okay, take a look at this drawing. Let me zoom in there. And here you can see I have carbon 1 bound to carbon 2. Carbon 1 has two H's, and it also has the symbol R, meaning a red atom. Carbon 2 is the consecutive carbon. Now, when you have carbons 1 and 2, any consecutive carbons that are sp3 hybridized are called vicinal carbons, from the Latin vicinity, in the area. Okay, for a Newman projection, suppose you have 10 carbons. Someone has to say to you, well, which Newman projection do you want? Carbon 1 to 2, 2 to 3, 6 to 7. You have to be told which is the particular vicinal pair that you want to investigate. Okay, here is a ball and stick model, and we're looking at it sideways. And you can see I have the red there and the blue up there, just like in the diagram. Okay, there it is. Let me reduce the magnification. All right. Now, if we're reading a textbook or a journal, we're seeing the structure. And many times we want to call your attention to one given bond with the groups that are attached to those carbons. And we want to look at the rotation and the energetics associated with it. Okay, so what we're going to do is put carbon 1 in front of carbon 2 with the ball and stick model. To draw a Newman projection, you first draw a circle, put a dot in the middle. Incidentally, that's a symbol for eternity, a circle with a dot in it. Then attach 3 bonds. The little one in front, the dot, is carbon 1. The larger the circle is 2. And carbon 2 will also have 3 bonds and also have the bond to carbon 1. So then carbon 1 has a red. It has 2 H's. Carbon 2 has a blue and 2 H's. And you have a Newman projection. Now I'll draw it more neatly over here. I draw these things so quickly, but that doesn't help you. Okay, there we are. That looks better. Red in front, blue in back, and the rest are H's. Now these could be H's, methyls, T-butyls, chlorines. They could be anything. Okay, let me zoom in on that. And that would be a Newman projection. Carbon 1 in front of carbon 2 in this case. Okay, then that's represented by this ball and stick model. Now I'll reduce the magnification so I can get this in field. Okay, now you can rotate around this carbon-carbon bond. Right now, the red and the blue are anti to each other. They're 180 degrees apart. You can't get any further apart for non-bonded groups than 180. That's called anti. Incidentally, the entire conformation shown here, this Newman projection with ball and stick model, is called the Staggered Conformation. And what that means is you don't have any anti-relationships. Rather, you don't have any eclipsed relationships. I'll show you that in a second. That's the staggered. And the object is to get the largest groups on carbon 1 and carbon 2 180 degrees apart from each other. Okay, if you have free rotation, 360 around that carbon-carbon bond, if free rotation is allowed. Now, you will see later on cases where it will not be allowed, but not now. Now, if I rotate, incidentally, you see the blue and this H. Let me hold that up. Okay, right there. The blue and the H, that is called a gauche relationship. It's 60 degrees. 60 is a number you come across a lot, 0, and also 180. And incidentally, these are dihedral angles. 4 consecutive atoms describes a torsional or dihedral angle. So right now, the blue and the red are 180 degrees apart, and we see a lot of gauche relationships. One here, one back here, one there, one there. The blue and the red, once again, are anti. Now, if I rotate this, I'm going to go to an extreme, and this is called an eclipse conformer, and that's bad news. Because what you have there, let me turn it one in front of the other. See, there's the red, there's the blue. They're now eclipsed. 0 degree dihedral angle, that's bad news. Because as the red and the blue go from hydrogen to methyl to T-butyl, that's going to restrict rotation 360 around the carbon 1, carbon 2 bond axis, because you don't want a T-butyl group syn or eclipsed to another T-butyl group. And you see the hydrogens are eclipsed. Now, chemists many decades ago assigned energy values, and we can say, all right, this eclipsing would cost 7 kilojoule per mole. This one's 11 kilojoule per mole. McMurray has a table with values ascribed to torsional. Remember torsional angle? Torsional strain is when you have a sigma bond eclipsed with a sigma. So that's what you're seeing. Let me turn this sideways. The blue and the red are eclipsed. We're looking at the Newman now sideways. There's a 0 degree angle between blue, black, and red. 0 degree torsional angle, dihedral angle. And you also have torsional strain because you have a sigma bond eclipsing a sigma. Steric is blue coming in contact with red. We don't have angle strain because we don't have a ring. So this is the Newman projection. You can do this with gumdrops and toothpicks. Now, if you're studying with me this summer remote, we also have viewers on YouTube. You can get toothpicks and colored gumdrops, and where there's a will, there's a way. You can do it. Just use the toothpicks for the bonds and different colored gumdrops. You can even use gummy bears if you like those, but roll them into a ball first. Do a little bit of a physics there by warming them up. Don't get them to melt, but to become a little more fluid. Okay, so that is what we're looking at. This is an eclipse conformer where we have hydrogen eclipsing hydrogen and the blue and the red eclipsed. This would be, you can have any number of conformers, with free rotation of 360. You could have a 10 degree rotation, 40, 50, 180. And certain ones, though, we call attention to. The staggered conformer, where you have a red and blue anti and a lot of gauches at 60 degrees. You can have eclipse and any infinite number, but generally we want to look for any eclipsing. We prefer anti, and we also are examining gauche. When you get to the 6-membered ring, you can apply a Newman projection to any 2 vicinal carbons in that 6-membered ring and be able to investigate what's attached around them. If you look very carefully in this chapter 3, you'll see cyclobutane portrayed with a Newman projection, and you'll also see, of course, the 6-membered ring where they might say, let's look at carbon 1 and carbon 2 as a Newman projection. The other 4 carbons then would just be considered groups attached to those 2. So Newman projection is meant to help you. And the other thing to remember, think about this, you can tie together 2 seemingly unrelated variables, Newman projection and naming of hydrocarbons. Let me write this one out for you. suppose you're studying for an exam, and this is one of the difficulties with organic when you're getting used to problem solving. Let me zoom in. Okay. Suppose you get this Newman projection. Now I'm going to draw. You never think about this until suddenly it's on an exam. And there's a methyl group here, and a CH2, CH3 there, and an H, and a CH3, and an H, and an H. Now you look at that. Okay? Now, what we have is a gauche relationship between this methyl and this ethyl. That's gauche, 60 degrees. The ethyl and this methyl are anti, 180 degrees apart. It's a staggered conformation, but ideally, we would like to be able to rotate that methyl away from the ethyl. Now, you could rotate around that carbon 1, carbon 2 bond axis. You could rotate, and you would be able to get away from them being gouged to each other. So that's something you want to think about. How to rotate that and get the lowest energy shape. Of course, the worst scenario would be methyl eclipsing ethyl. Either this methyl or this one, rotating to eclipse that one. So what you want really is to get that methyl away from ethyl, but you don't want to really eclipse methyl and H. Eclipsing is not a good thing. You want to stay away from that because you have torsional strain and steric strain. Now here's the other thing. What's the name of this hydrocarbon? See, with the Newman projection. So what you do, you put carbon 1, I'll show this in a minute. Carbon 1 bound to carbon 2. Carbon 1 has a methyl and a methyl. I'll put one there and put one there. And what else? Carbon has an H. It's also bound to carbon 2. Carbon 2 has an ethyl. So that's CH2, CH3, and it also has 2 H's. So now let me show you that. I just drew out the corresponding hydrocarbon, and the name, well, single longest chain, 1, 2, 3, 4, 5, 2-methylpentane. I'll write it as CH3. Now, this is the type of thing in organic that students are not prepared for. See, there's the structure, 2-methylpentane, and that is portrayed in this Newman projection. This often catches a student off guard. You're being asked to utilize 2 seemingly unrelated variables, naming hydrocarbons and Newman projection. So you think about that. There's a lot to do with this. And once again, gumdrops, toothpicks. Let me zoom in or zoom out. And you just work on rotating this. You don't have to commit to memory with me the cost factors for a methyl on methyl or a methyl on H. We can refer to those numbers. We can look them up. The important thing is to realize that as you do a 360, you're going to go from low energy, red and blue anti, to the highest energy conformer, where blue and red are eclipsed. Okay, hold it just like this. All right, so the next thing, I will upload information from chapter 4, and that is going to be your stereo chem, 3-dimensional chem, left and right-handed, a very important chapter of the heart and soul of molecular pharmacology. And that'll be the next little video I put together. Thanks for watching. Bye for now.